Hi everyone, this is the topic of linear modelling. It's a topic for the International Baccalaureate course Mathematics Standard. In this topic we're going to look at correlation and in particular Pearson's correlation coefficient. Then we'll look at line of best fit and least squares regression lines, and we'll finish off with interpolation and extrapolation. Now, two variable statistics is called bivariate data, and it involves the analysis and display of two variables. We can still calculate the same statistics like mean, mode, median, range, interquartile range and standard deviation, but we're going to learn to calculate some new statistics as well, like R, which we'll go into what that is in a minute, and linear regression lines. When we graph two variable statistics, we use a scatter plot like this. So here you can see my two variables, height and weight, and each of these are an individual person. So this person's height is about 1.475 or something like that, and their weight is 52. And so we just plot on both axes a single point. And what we're pretty much going to be doing for this entire topic is seeing if we can find a relationship between these dots, where these dots fit either a straight line, which looks like it might well be in this case, or a curved line. Of the two variables, one is usually an independent variable and the other is a dependent variable. And we always place the independent variable on the horizontal axis. So in this case here, we've got a study about the outside temperature and what happens with the sales. So as the temperature increases, the sales pretty much go up. In this case, the temperature is the independent variable. Nobody is controlling it. It is what it is. The temperature is controlling the sales. So sales is dependent on temperature. So here's our independent variable and our dependent one. Back to the graph we had before, it's difficult to say whether height or weight is an independent or a dependent variable. We've put height down here as if to suggest that the height is causing the weight, which to a certain extent, probably the taller you are, the heavier you are. So in this case, the height will be the independent variable and the weight will be the dependent variable. Now, correlation refers to the relationship between the two variables. And we refer to the following when we're describing the correlation: the direction, the linearity, so is it a straight line, the strength, how close are the dots to the line, are there any outliers, and causation, which I'll get to later. So these scatter plots show positive linear relationships of varying strengths. So here we're talking about the direction. They're positive, they're going up from left to right in every case. They're roughly linear, they're roughly a straight line in each case. This one is very strong, almost perfect. Almost a straight line, I think, could probably be drawn all the way through there without any of the dots deviating. This one is moderate or moderately strong. So a line through the middle there, the dots are a little bit away, and this one's much weaker. But you can still see the relationship here. This scatter plot shows no relationship. These ones here are negative, they're also linear, and they're varying strengths. Weak, moderately strong, strong, probably perfect. This scatter plot shows a negative, moderate, nonlinear correlation. So it's negative because it's going down from left to right. It's moderate because it's not all sitting on a straight curve, and it's nonlinear. It's curving around. There's also a couple of outliers that we can see. Now, causation. Just because two variables have a high correlation doesn't mean that one causes the other to happen. If a change in one variable causes a change in the other variable, we say there exists a causal relationship between them. And here's a couple of comics that I'm going to show you. This one says, "I wish they didn't turn that seatbelt sign on so much. Every time they do, it gets bumpy." But of course we know the seatbelt sign is not causing the turbulence. Okay, it actually happens because of the turbulence as well. So there's no causal relationship between the seatbelt sign and the turbulence. Here's another one. So the top comic says correlation, 100% of people who breathe die. And the bottom one, which says causation, says 100% of people who don't breathe die. Can you see the difference between the two? In the top one, just because you're breathing doesn't mean you will die. It's not causing you to die. It just happens to be a perfect relationship. If you are a person who breathes, you will eventually die. The bottom one says 100% of people who don't breathe, so if they're stuck underwater without any oxygen, will definitely die. So the not breathing in the second case causes the death. Hope that makes sense to you. Let's have a look at how we measure correlation. So we can calculate a statistic to help us determine the strength of the correlation between two variables. It's called Pearson's correlation coefficient. It's given by that horrendous looking formula there. And it's got the symbol R. So in the first place, we're finding, in this case, we've got two variables, x and y. We're finding the difference between x and its mean, the difference between y and its mean, multiplying them together and doing the sum. Then on the denominator, we're finding the difference between x and its mean and squaring it, and then doing the sum. And then we're doing the difference between y and its mean, squaring them all, adding them all up, multiplying those two and doing the square root. Goodness me. So that gives us roughly what this is doing actually is finding the average distance that every point is away from a straight line that goes straight through the middle. Now R goes anywhere between -1, which is the perfect negative relationship, so a bit more perfect than this one, so where all the dots are on the line, all the way up to +1, so a bit more perfect than this one, all the dots are on the line. So anywhere between +1 all the way through to 0, no relationship, and then all the way up to -1 or down to -1. Now one thing that you need to know is how to calculate R by hand. And to do that, you're going to need the following columns. So here's our first variable and the second one. We need to know the mean in each case. And then this column subtracts the mean, the x mean, from x. This one subtracts the y mean from y. Then we need the product of these two, and we need to square each of these columns. So there's all the data, all the calculations. Once we've done that, we need to sum this column here and then these two as well. So our formula, we want the sum of the x minus x bars multiplied by the y minus y bars, which is that one there, and then divided by the square root of this sum, which is that one, multiplied by this sum, which is this one, and put that in, and we get 0.863. So on the calculator we select stats and we enter our first variable into list 1 and our second variable into list 2, like this. Then we hit F2 for calc and this will come up. Now, a couple of really important points. We never have to change the frequency to another list. Remember how we had to do that with one variable statistics? So we might have had, with one variable we have only the x, and we had an f here, and we had to change it because we had 6 noughts, for instance, and 2 ones. So we had to go in and change the frequency to list 2. We never have to do it in this case because there's only one of these, and there only ever will be one. I mean, it would be a coincidence if there were 2, another one sitting down here, and you'd just enter that again if that happened. So there's only one time where it's 80 and 94. There's only one time where it's 60 and 88. So the frequency in this case is set to 1, and that's correct, and it'll always be 1. So you can ignore this button for 2 variable statistics. All right, second point of confusion. You'll be very tempted to go into here. If you go in there, that'll give you the means of each set of data, but it won't give you what we want, which is in this case is R. So Reg stands for regression, which we'll get to in a minute, and that's where you want to go into. So we hit F3 for Reg. Then you hit F1 for X, And then what will happen is it'll come up with one of these two. It doesn't matter which one you use, it'll just change the form of the line. It's not going to matter for R at all. So I would suggest you always use F1 for AX plus B. So we're going to there, and we can see R here. So it's 0.863. Okay, let's move on to the line of best fit. A line of best fit endeavours to represent the data points fairly. When we go to draw a line of best fit, we calculate the mean point. So that's the mean of the x's and the mean of the y's, and we plot that point. And then we draw a line through the mean points so that the spread of points above and below the line is fair. Here's an important point. The line of best fit is not accurate. It'll vary from person to person. So the one thing that's important is that it goes through this mean point and that it looks like it's distributing the points above and below fairly. So here we've got some data, we've got some temperatures and some time limits. So here's the independent variable and here's the dependent variable. So we're going to take the mean of the times and the mean of the temperatures and plot that point. So this is the scatter plot, and that's the mean point just there. So now to draw the line of best fit, we just put a line through it so that the number of points on this side is sort of equal to the number of points on this side. And as I mentioned before, it'll vary from person to person. But we can create what's called a least squares regression line. And this is where it will be fixed for a set of data, so it won't vary from person to person. So the least squares method finds the distance that each point is from some line that's not determined yet. It squares those distances to get rid of the negatives and then determines the best line so that all of those, sum of those distances is minimized. So we can use the calculator to find this line. Again, we enter the two variables into list 1, list 2. We go F2 for calc, F3 for reg, which is regression line, F1 for x, and then we're going to choose F1 for AX plus B. That will give us this again. There's our R, and here's A, which goes in there, and B, which goes down here. So our linear regression line is y is equal to 0.516x plus 48.3. One thing to note here, I've written both of these to 3 significant figures. So remember, in the IB, we need 3 significant figures or more. Once we've got the linear regression line off the calculator, we can change the variables. So we can define the variables for our own particular experiment that we're doing. So we could say, let T be the time devoted to revision in minutes, and let E be the exam score out of 100. And so now instead of Y and X, we can change them to E and T. If you're confused about which is which, this is X here, they're alphabetic, this is Y. So instead of revision time, we're writing T. Instead of exam score, we're writing capital E. So you can see where that's going to go in here. So we would write E is equal to 0.516t plus 48.3. Now once we've formed our linear regression line, we can use the equation to estimate values. That's the whole reason that we do it. So we are using algebraic modelling. We're finding an equation that models the data. Now there's a couple of things to note though. Here I've got a new example. We've got some temperature, the outside temperature, and what happens with the sales in a particular store when the temperature goes up. So it's a pretty good relationship. It's pretty strong. We can see also the line of best fit through there. So if the X values that you use, so that's the temperature, in your linear regression line, lie within the data set, so in between these 2 points, then we call this interpolation. Now these 2 points here are called the poles of the data. So they're the edges. So if I'm inside here, it's called interpolation. If I'm outside the poles of the data set, then it's called extrapolation. Now, not surprisingly, in here, any sort of answers that we get when we're estimating values are going to be fairly reliable because we've got data points to support that. But outside these poles, it's not reliable at all. We don't really know what's going on outside there, and I'll show you an example in the next page. Let's return to this example. Find the predicted exam score if a student studies for 50 minutes. So here's our formula. E is equal to 0.516t plus 48.3, and I'm going to substitute in t is 50. So this tells us that if I study for 50 minutes, then I can expect an exam score of 74 out of 100. This is an example of interpolation because the 50 lies within the poles of the data set. So it's relatively reliable and valid. This one's not. If a student studies for 160 minutes, their predicted exam score is 131. And remember, that's out of 100. So why does the model give a ridiculous exam score for this time? Well, it's because this is an example of extrapolation. This 160 minutes lies outside these revision times. So we don't have any idea what will happen if a student studies for 160 minutes. So this is an example of extrapolation. The model is not reliable beyond the poles of the data. Just before we finish, here's a glossary of the words that we learned, because there are quite a few in this topic. Bivariate data means it's got two variables. The independent variable is the variable that doesn't depend on another variable, whereas the dependent variable is the one whose value depends on that of another variable. Correlation refers to the relationship between two or more variables. Causation means that one variable causes changes to the other variable. Line of best fit is a line drawn through a set of data points so the spread of points below and above the line is even. The mean point is the average of each variable. It's plotted as a point. Least squares regression line is a method of forming a line of best fit so the distances each point is from the line is minimized. The poles are the extremities of the data. Interpolation means using a line of best fit where the independent variable is between the poles, and extrapolation means using a line of best fit where the independent variable is outside of the poles.